channel. Today we're going to look at, we have a physics content to look at. We are working on past questions on this topic. We already studied this topic in our channel, energy quantization and photoelectric effects. So if you have not watched those videos on energy quantization and photoelectric effects, please go to the channel and then look for the videos where these topics we are taught, and then download them and be able to study along with us. If you are not subscribed to the channel or you are seeing the channel for the very first time, please subscribe. How do you subscribe? Go to the channel's profile picture. Under the profile photo, you're going to see the channel's name, Best Science Brain. Then under the channel's name, you see a small bell, a tiny bell. Then you tap on that bell once and get subscribed. Tap on it once and get subscribed so you can see our videos. So today, we're going to look at some past questions. This class is meant for those in senior secondary school 3, high school 3 or SS3, for those who are writing their UTME and post-UTME, and also for those doing general physics in their first year of higher institution. That will also help you to understand electronic or atomic physics. So let's go to this question on the board that says, if light with photon energy 2 electron volts is incident suitably on a metal surface with a work function of 3 electron volts, then, let me repeat the question again. If light with photon energy of 2 electron volts is incident stably on a metal surface with a work function of 3 electron volts, then option A, no electron will be emitted. Option B, the few electrons emitted would have a maximum kinetic energy of 1 eV. C, the few electrons emitted will have a maximum kinetic energy of 3 electron volts. D, many electrons will be emitted. So this is UTME, Unified Tertiary Matriculation Examination 1994. So let's go to the question. Let's look at what we need. They give us the photon energy. The energy of the photon, written as E, is 2 electron volts. They gave us the work function. The work function is 3 electron volts. And you know that the energy of the photon or the light that falls on the metal given by the work function plus the kinetic energy. That means the energy of the photon should be higher than the work function. So the sum of these two will give us the energy of the photon. So since in this aspect, the energy of the photon is less than the work function, that means no electron will be emitted. The answer to the question is option A. No electron will come out because the photon energy should be higher than the work function for electron to come out. Remember, the work function is the minimum amount of work done to remove an electron from a metal surface. So the answer is option A. Going to number 2 over there. Number 2 says, a light of energy 5 electron volts falls on a metal and electrons with maximum kinetic energy of 2 electron volts are ejected. The work function of metal is a light of energy 5 electron volts falls on the metals and the electrons with maximum energy of 2 electron volts are ejected. The work function of metal is, okay, the energy of the light falling on the metal is 5 electron volts. The maximum kinetic energy, that is Ke, is 2 electron volts. We have to look for the work function. Now, based on Einstein photon equation, energy of photon given by kinetic energy plus work function. We now make work function the subject. Work function now becomes the energy of the incident radiation minus the kinetic energy. So that's going to be 5 minus 2 minus 3 electron volts. So the work function of the metal is 3 electron volts. Going to the question, option C is the answer. And this is UTME examination 1995. Going to number 3 question that says the energy associated with a photon of a radio transmission at 3 times 10 to the power 5 hertz is, so looking for energy of photon, and then this value 3 times 10 to the power 5 hertz represents the frequency of the radiation. So how does energy connect to frequency of radiation? That is the Planck equation, which you give by E equal to Planck constant times frequency, which will land under energy quantization. So energy now becomes the Planck constant given to us in bracket as 6.63 power minus 34, then times 3 at power 5. Multiply them together. So that gives us, if you multiply this, we'll have 19.89 times power minus 34 power 5. So multiplying 3 by this, you have this. So convert to standard form. 19.89 is 1.989 times power 1. This gives you back this. Then bring down minus 34 and then 5. So that gives us 1.989 times, take one base, since they have same base, put log in this is 10, 1 minus 34, and then plus 5. So when we do that, we're going to have E to be equal to 1.989 times this power minus 28. 1.989 power minus 28 joules of energy. Or approximately, this is 2 power minus 28 joules as our answer. So let's look at the answer. The correct answer to this option is, this question is D, 2.0 power minus 28 joules. UTME 2002, University Unified Tertiary Examination 2002. So the answer there is option D. So going to the next question, number 4 there, says an electron makes a transition from a certain energy level E to the ground state E0. The frequency of emission is 8.0 by power 14 Hz. The energy emitted is, so let's look at this problem. An electron makes a transition from a certain energy level EK to the ground state E0. The frequency of emission is 8.0 times power 14 Hz. The energy emitted is, look at this question, let's go to the solution. So let's take this as EK. This is the ground state. So emission is from EK to ground state. And the frequency of radiation given to us as 8.0 power 14 Hz. We have to find the energy of the emitted radiation. Going by Planck equation, given by HF. Planck constant given to us as 6.6 power minus 34. Then multiply by this frequency, which is 8 power 14. When we solve, the energy emitted is going to be 5.28 times power 5.28 power minus 19 joules. 5.28 power minus 19 joules. So you go to the question, the correct option there is option B for this question. So watch our work and remain focused as we go to the next aspect of this video. 5 question that says calcium has a work function of 3 times power minus 19 joules. The maximum energy of liberated electrons it is illuminated by light of frequency 6.7 power 14 Hz is, repeat the question, calcium has a work function of 3 times 10 to the power minus 19 joules. The maximum energy of liberated electrons when it is illuminated by a light of frequency 6.7 times 10 to the power 14 Hz is. Now we look at this problem now. We know that energy of photon is given by, or energy of the cell radiation given by work function plus kinetic energy. And we're looking for the maximum energy of the liberated electrons. The electrons are liberated, they will possess what we call the kinetic energy. So our Ke is what we're looking for. Will now become energy of photons minus work function. In this question, we're already given the work function. So we need to find the energy of the photons. So energy of photon given by Planck constant times frequency. The Planck constant is 6.6 power minus 34. And the frequency of the radiation is given to us as 6.7 to the power 14. So apply these two together. We now have the energy of radiation as 4.42 to the power minus 19. So this is the energy of radiation, of the radiation that falls on the metal casing. They were looking for the energy of the electron, that is the energy. So our Ke now becomes equal to energy of the radiation, which is 4.42 power minus 19, then minus the work function. In the equation, work function is 3 to the power minus 19. That is 3 times 10 to the power minus 19. That's the work function. We can factorize 4.42 minus 3. Then times 10 to the power minus 19. Solving this, we're going to have 1.42 power minus 19 joules as our answer. So this is the energy of the liberated electrons, because when electrons are liberated, they will possess, they'll be in movement or motion, they will now possess kinetic energy. So the answer to the question is option A. That's our right answer to this question. So you can go through our work before we go to number 6. We'll now go to number 6. That says the work function of a metal is 4.375 electron volts. Calculate the threshold frequency of the incidence radiation. Work function is given to us as 4.375 electron volts. We're looking for the threshold frequency, which is written as F subscript O. And you know in physics, work function is given by Planck constant times threshold frequency. And then the threshold rate now becomes work function over the Planck constant. Before we do that, the work function must be converted to joules. This is not in the standard unit. So our work function now becomes 4.375 times, convert to joules, multiplied by the conversion factor, but times 1.602 power minus 19. So the value of the work function, when multiplying that, will give us 7.01 times power minus 19 joules. So going to this formula now, our threshold frequency now becomes the work function substitute 7.01 power minus 19 over the Planck constant given to us should be around 6.6 power minus 34. So we'll divide this value. We're going to get 1.06 that's power 15 Hz. That becomes our threshold frequency. So you go into the options. Option B is the right answer to the question on the board. So go through our solution. Our Number 7 says the work function of a metal is this. Work function is 8.60 power minus 19 joules. We have to determine the maximum wavelength. The maximum wavelength of the incident radiation required to eject electron from a photoelectron from the surface of a metal. The maximum wavelength required of incident radiation required to eject a photoelectron from a metal surface is called the threshold wavelength. I repeat myself. The maximum wavelength of radiation required to remove electron from a metal surface is called the threshold wavelength. While the minimum frequency of light required to remove electron from a metal surface is called the threshold frequency. Minimum frequency of radiation required to eject electron is called threshold frequency. While maximum wavelength of radiation required to remove electron from a metal surface is called the threshold wavelength. So we are looking for the threshold wavelength in this question. So that is it. Now know that work function begin by Planck constant times threshold frequency. Remember that from velocity equation you have lambda times frequency. But because the speed of light is constant, we replace this v with c. So since we are dealing with how does this wavelength and frequency? So how does threshold wavelength connect to threshold frequency? You can say C equal to threshold wavelength times threshold frequency. So you can see this modification. So we're now trying to make FO the subject. FO becomes C over threshold wavelength. Okay? C over threshold wavelength. Now go to this formula. Work function is Planck constant times threshold frequency. Substitute this into this equation. Work function now becomes Planck constant times C over threshold wavelength. We are looking for the threshold wavelength. Let me this out of the board. Making this one the subject. We now have threshold wavelength equal to C over work function. How do we get this? Go back to this, cross multiply, and make threshold wavelength the subject. You come to this. So now make our substitution. Our Planck constant is 6.63 power minus 19, giving the equation. Then the speed of radiation is given to us here as 3 to the power 8 all over the work function, which is already in joules, 8.6 power minus 19. So when we solve this, we get our threshold wavelength. And the answer to the equation is 2.3 to the power minus 7. 2.3 power minus 7 meters. So these are threshold wavelength. Option C is the right answer. So you can go through our work and then understand from beginning, understand how it is done. This one more problem on the board for today's lecture. Consider that sodium has a work function of 2.30 electron volts. Determine its one threshold frequency. So how many questions following this particular number? So but we'll take the one after the other. So let's go to the solution. For number 1, we are given the work function as 2.30 electron volts. So we're going to first of all convert this to joules. How to convert to joules? You multiply 2.30 by the electron volt value in bracket. Electron volt is 1.60 to the power minus 19. Now say 1.602 to the power minus 19. Convert it to joules. We multiply. We're going to have 3.685. 3.685 power minus 19 joules. So that's the work function. But that question one says we should find the threshold frequency. So that's the question there. So work function again by Planck constant multiplied by threshold frequency. So the threshold frequency now becomes work function over Planck constant, which is 3.685 minus 19 over Planck constant, which is given to us in bracket as over there, down, 6.626 power minus 34. So come back. So making the substitution, we'll have this work function down, then the Planck constant, then dividing. Our threshold frequency is going to be 5.561 or 5.56 per 14 Hz. So this is the threshold frequency of the incident radiation. Number 2, II says we should find the maximum kinetic energy of the photoelectrons. So before we go over to number 2, take a look at our solution before we go to number 2. Maximum kinetic energy of the photoelectrons. Okay, so going to number 2 now, we want to look for Ke, the energy of the photoelectrons. To get Ke, remember that from Planck-Einstein equation, that energy of photon given by work function plus kinetic energy. So that is what we need. And then, do we have our work function? Yes. Our work function is given to us there. Okay, the question is not yet complete. Calculate the maximum energy of the photoelectrons produced if sodium is illuminated by light of wavelength 5.0 to the power minus 7 meters. Okay, let's go back. Now, for us to solve this, we need to get the energy of the radiation. Energy of radiation given by the formula H, Planck times frequency of radiation. I will know that frequency is velocity over wavelength. So, going back to this, energy of radiation given by H, replacing frequency with a C over lambda. C over lambda. So we have to calculate the energy of radiation first before we go back to this formula. So the Planck constant is given to us as 6.626 power minus 34. Is given to you in bracket. And the speed of radiation given by 3 to the power 8. Let's go back. So you substitute times 3 to the power 8 all over the wavelength. The wavelength, go back to question II. The wavelength of light is what? 5.0 power minus 7. Now we'll come back 5.0 power minus 7 to get the energy of radiation. So when we solve this, the energy of radiation is going to give us 3.98 power minus 19. So the energy of radiation, not yet the answer. We're looking for the kinetic energy of the photoelectron. Before then, we need to find the energy of the radiation. We find the energy of the radiation. So we're looking for Ke. Before then, we need to find energy of radiation. So having done that, let me wipe this side. From this formula, we see that energy of radiation or photons given by work function plus Ke. We made this one the subject. So looking for the energy of electrons. Ke becomes energy of radiation minus work function. Energy of radiation, E, is this value, 3.98 power minus 19. Work function, which we are gotten before in the first problem, our work function, we got it as 3.685. 3.685 power minus 19 also. When we converted the 2.3 to joules, we got that. So we now have 3.98 minus 3.6 factorizing, since they have the same exponential, and then multiply by power minus 19, only one. So if we solve this, our final answer is going to be 2.95, that's power minus 20, as the energy of the kinetic energy of the electrons, 2.95, that's power minus 20 joules. So having done that, we go to question number 3, that says we should find the maximum velocity of the photoelectrons. The velocity of the photoelectrons. Now, in question 2, we got the kinetic energy of the electrons. We're now looking for the velocity of the photoelectrons. How do we get that? We know that our kinetic energy in physics have mass times the square of velocity. So make the velocity the subject by cross multiplying. This is just writing mv squared over 2. Cross multiply, we have this, we have that. We now have mv squared equal to 2ke. Then v squared equal to 2 times kinetic energy all over mass. Then velocity now becomes square root of 2ke over mass. So we're going to solve this. So how do we solve it? We go up there and then make our substitution. Velocity is square root of 2 times the kinetic energy of electron all over mass of the electron. So we now have equal to 2 times the kinetic energy is what we got before as 2.95 power minus 20. The mass of the electron is given to us in bracket, that's the ME, 9.109 power minus 31. So when we solve and evaluate that, the velocity of the electron will now be giving us 2.53 times 10 raised to the power 5 meter per second. So that's the velocity of the electron. We go through our work before we go to the last question of today. So last question of today says IV, the stopping potential of the photoelectrons. We have to find the stopping potential of the photoelectrons. Now question IV. So we'll go back to the whiteboard. Remember, in our initial, when we study this topic, you go and watch the video if you have not done that on photoelectric effect, the tutorial. I told you that electron charge times stopping potential will give us the kinetic energy. So we're looking for the stopping potential. Stopping potential is going to give us the kinetic energy of the electron divided by the electron charge. So the kinetic energy of the electron is 2.95. We have earlier calculated minus 20. The electron charge is the value you have there, the electron volt, 1.602 power minus 19. So when you divide this, what you're going to get is the stopping potential. You're going to get 0.184 volts. That becomes our stopping potential. So with this, we have done justice to past questions, both JAM and WAEC questions and other examinations involved here on energy quantization and photoelectric effect. And I believe that with these examples we have taken so far, you'll be able to tackle some problems on energy quantization. In our next topic, we're going to move over to X-ray and the Broglie principle, equation, and some other aspect of atomic physics. So always stay connected, share our videos to friends and to class groups so that need this video. You'll be helping somebody by doing so. Thank you.